Very good morning to all of you. In the last lecture, we have seen how we will be able to approximate an inverse for an invertible matrix A by using Neumann series. Okay, our main goal is to find the solution for AX, the system of linear equation which is given by AX equals to B. Okay, due to the limitation on computer, okay, when you write a code for solving the problem by using Gauss elimination method or any other direct method, though it is of with finite number of steps, okay, but due to the round of errors and due to the fact that computer has finite precision, you will not be able to get an accurate solution or exact solution. X of 0 be an approximate solution of the above system. Okay, means this implies, okay, okay, AX0 is approximately equals to B. Okay, right. Further, let X be the exact solution. X be the exact solution. Then you can write X as equals to X0 plus the error term, which we are denoting by E superscript with 0. So here, if you recall what is E0 is, if you see here, it is equals to X minus X0 is called the error vector. Okay, and if you write it further, this is equals to X equals to A inverse of B minus A inverse of A X0. Okay, right. Further, if you write it clearly, E of 0 is equals to A inverse of B minus AX0. Right? So, if you recall, this is, we have denoted by R with, because it depends on superscript 0, so we are also making here also superscript with 0. This is called the residual vector. Okay, so here you are solving the, so this implies A0 is equals to R0, right? So if you look at it carefully, so you have to get the residual vector R0 equals to B minus AX0. Then you will solve this equation AE0 is equals to R0, and then you are going to get, and you have this from the previous relation X equals to X0 plus E0, so you get the exact solution. Okay, but again, this, because of this process, here you are going to use again Gauss elimination method or another technique to solve this. Okay, we are not going to solve because of the computational limit. Okay, and because of the cost of finding the A inverse of the matrix, we are not going to solve the equation directly E of 0 equals to A inverse time R0. Rather, we are going to solve the equation. Rather, we are going to solve this equation by AE0 is equals to R0. Okay, by using Gauss elimination method with or without pivoting. So still it will have some error. So this is going to be get a new refinement of x. Okay, so once you have x1, then you will, so this is your, you have step 1, which will give you the refinement of the previous approximation, better refinement. Then similarly you will have the step 2 is, you have now r1 that is equals to b minus ax of 1. Then ae1 is equals to r of 1. Then you have to solve this equation. Then you will get the new refinement, which is given by x of 2, that is equals to x of 1 plus e of 1. So now the success of this method depends on where? Okay, the success of this method depends on, you are going to generate the sequence of, okay, so in this method you are going to generate the sequence of approximation, x of 0, x of 1, x of 2, x of 3 and so on. Okay, and if you write the method, okay, xk plus 1 is equals to xk plus ek, but that is equals to A inverse B minus axk. So if you rewrite the above, so you have k is equals to 0, 1, 2, 3 and so on. Now as told earlier, we are not going for finding the inverse of the matrix due to the computational limit. So what we are going to do is, we are going to replace A inverse by an approximate inverse. So by using the Neumann series that you can do. So this implies, so you have the scheme is xk plus 1 is equals to xk plus b time b minus axk. So b is an approximation of inverse of the matrix. Okay, now let us assume that this generate this scheme, which is given by 1, generates a sequence of approximation, and this converges to the exact solution. Okay, so let limit of xk goes to the exact solution. Then what will be the condition we will have? Okay, right. Since this is system of linear equations, so if limit xk converges to x, so axk will converge to ax. So then 1 implies, after applying limits, you can say after applying limit on both sides. So what you will get is, you are going to get x equals to x plus b time b minus ax. So that is 2. Now from 1 and 2, what you will get is xk plus 1 minus x equals to xk minus x plus, so b will cancel, so you have, this is a minus ba time xk minus x. If you go back and check it carefully, so this is equals to, if I write, this is I minus ba xk minus x Now if you keep on applying this successive relation, okay, recursive relation, then you will get this is equals to I minus BA to the power k plus 1 times x of 0 minus x. Now this will imply if you take any subordinate matrix norm xk plus 1 minus x is less than equals to norm of I minus BA to the power k plus 1 and use the sum multiplicative property times norm of x of 0 minus x. Now when this will, so you have now the question is when this tends to 0 as k tends to infinity. So there is a question mark. So whenever this norm of I minus BA is less than 1. Okay, so whenever, so from here what we can do, so when if norm of I minus BA is less than 1, then I can say limit k tends to infinity, norm of xk plus 1 minus x is equals to 0. Now not that. So if I use the Neumann series, so not that norm of I minus BA less than 1 implies BA is invertible, right? By the using definition of Neumann series, this implies both A and B are invertible using the determinant property. And since Neumann series implies, so now you can say Neumann series implies BA inverse is equals to summation k equals to 0 to infinity I minus BA to the power k. Now since B into A inverse is A inverse B inverse, okay, so this implies A inverse B inverse is equals to summation k equals to 0 to infinity I minus BA to the power k. So now we not that B inverse, we have assumed that is the approximation of the inverse of A. So if you further write from here B inverse, so this implies B inverse is equals to A times the summation k equals to 0 to infinity I minus BA to the power k. So you can choose here, okay, so you can choose a large number when you use the computer, because computer does not understand what the meaning of infinity. Okay, you have to choose n number, n large. Okay, so you are going to approximate inverse by, you can say this is A times summation k equals to 0 to capital N I minus BA to the power k. So you have to choose n sufficient large so that it will give you the good approximation of A inverse. Okay, right. So this is the process of iterative refinement. So it will be converges, okay, that the process what we have defined above, it converges as long as norm of I minus BA is less than 1. The next topic is iterative methods for solving system of linear equations ax equals to b. So as the name itself tells that they are iterative in nature. So first question is, why do we need these iterative methods? Okay, what are the advantages of these iterative methods? So if you look back, the direct method gives you the solution in finite number of steps, right? However, iterative methods will generate a sequence of vectors or solutions, approximate solutions that converges towards a solution. So when you are working with the large system and you are worrying about speed and storage in computer memory, there the iterative methods have decisive advantages over direct methods. So therefore, for large systems, they are oftenly used. The next thing is, they are usually stable and actually dampen errors as process continues. So to design iterative methods, okay, let's work out with an first one example. Okay, let's start with an example for solving the system. Let's say this is 3 1 2 4 time x1 x2 is equals to 4 and 6. So it's very clear that x1 equals to 1 and x2 equals to 1 is the solution vector for this system. Now if you write this in the following forms, I have two equations. So I have here two equations. One equation is 3x1 plus x2 equals to 4, and the another equation is 2x1 plus 4x2 equals to 6. Right. Now if I rewrite these two equations from here, if I wish to write here, so x1 equals to 1 by 3 times 4 minus x2, and x2 equals to 1 by 4 times 6 minus 2x. So I can rewrite the above system in the following form. Now what we are going to do is, we are going to write the scheme now. x1k plus 1 is equals to 1 by 3 4 minus x2k, and another equation is x2k plus 1 is equals to 1 by 4 times 6 minus 2x1k. Right? Now we can write the above equation in the following iteration scheme. So the way we have written this has some adaptive ways. Okay, so we should start with some approximation. So we are starting with, you can say, x1 0 comma x2 0. So initial approximation, good approximation is required. Okay, so you can use for a good approximation, either you use the Gauss elimination method or decomposition method, or you can fix the initial approximation as 0 0. Not that we are supposed to design an iterative method that should converge with that converge where the initial vector can be any arbitrary vector. Okay, so you take any initial approximation and that should converge to the solution. So with that assumption, with that goal, we are starting with here 0 0. So then x1 1 is equals to 4 by 3 and x21 is equals to 6 by 4, that is equals to 3 by 2, that is equals to 1.5, and that is equals to 1.33 n. Now if I wish to get now x12 is equals to 1 by 3 times 4 minus x2 of 1, that is 1.5, okay, and that is equals to 0.833, and x22 is equals to 1 by 4, 6 minus 2 into 1.3, .8335. So if you use x11 and x21, then you have the x12, x22. Other iterated values for further steps are given by as follows. So now if you look at the pattern, okay, so if you look at the values of x13 and x23 and x14 and x24, they are getting towards closer to 1 only. So this method is called Jacobi's method, improvement of previous method, which we have actually seen that is converging towards the solution. So for the example, x1 of k plus 1 is equals to 1 by 3 times 4 minus x2 k, and x2 of k plus 1 is equals to 1 by 4 times 6 minus 2 times x1 of k. So you have started with an initial vector x1 of 0 comma x2 of 0 as 0 0. So what you can do here is, once you are going to use this here to get x11, so you have, so once you use this, you are going to get x11. Then for evaluating x2 of 1, you are going to use, instead of x1 0 comma x2 0, so I prefer to go for improved value of x1. Okay, so if you do so such method is called Gauss-Siedel method. Gauss-Siedel method. Once you use improved value in the same step itself, okay, once it is improved, you are going to replace that vector, okay, or you replace that element or that coordinate, okay. So x1 0, once you use this in getting x11, you are going to use for x11 instead of x10 for evaluating x2 of 1. Okay, so if you do so, x11 is equals to 1 by 3 times 4 minus 0, that is equals to still 1.33, and x2 of 1 is equals to 1 by 4 times 6 minus 2 into, not 0 here, we are going to use the improved value 1.33. Okay, so similarly for the next step, okay, similarly for the next step, so 0.835. So for the next step, when you are going to get x1 of 2, so that is equals to 1 by 3 times 4 minus 0.835, that is equals to, if you get it by calculator, is equals to 1.055 and x2 of 2 is equals to 1 by 4 times 6 minus 2 into, so I am going to use here the improved value of x1, that is 1.055 instead of 1.33. Okay, so that is going to be 0.9725. If you go back and check, okay, then you have got this much closed value in the two steps itself. Rather, you are going in the previous, if you apply the previous method, you are getting in the fourth step. Okay, so you will see when you will decide the rate of convergence for iterative methods, you will find that this has double speed than the Jacobi's method. Okay, right.